Give me 20 minutes, and I promise you, hypothesis testing will click forever. You're about to master the universal algorithm, the one algorithm that powers every A/B test, every clinical trial, and every quantitative trading strategy. First, let's learn the language. It's actually pretty simple. First up is H0, the null hypothesis. This is just the boring status quo, the default reality. Then you have H1, the alternative. This is the exciting new theory you want to prove. Next is alpha. Think of this as your BS threshold. It's the maximum risk you're willing to take of being wrong, and we usually set it at 0.05. And finally, the p-value. This is the probability of seeing your data if that boring null hypothesis is actually true. Here's the secret. It's just 4 steps. So what is this universal algorithm? It's a function. It takes your data and it spits out a decision. That's it. Step 1, formulate. You define H0, your boring theory, versus H1, your exciting theory. Step 2, calibrate. You set your alpha, like 0.05. This is where you ask yourself, how much evidence do I really need? Okay, so we formulated and calibrated. What's next? Step 3, compute. This is where you calculate a test statistic. Now, look at this formula here for Z. Don't worry about memorizing it right now. All it's doing is measuring how far your data is from that boring null hypothesis. How weird is your result, really? And that brings us to the final step. Step 4, decide. This is the moment of truth. You compare your p-value to your alpha. If your p-value is less than alpha, your result is just too weird to be random chance. You get to reject H0. Your new theory wins. But if the p-value is greater than or equal to alpha, well, it could just be random noise. You fail to reject H0, and the boring status quo remains. Now, you've probably heard of a whole zoo of different tests, and it seems really overwhelming. For example, in this table, you see that for continuous data with a large sample size, you use a z-test. For a small sample, a t-test. And for categorical data like clicks, you'd use a chi-square test. But here is the secret, the most important thing you need to know. The algorithm never changes. The only thing that changes is the syntax, the specific formula you plug into step 3. So now that we have the framework, let's build some real deep intuition. We'll begin with step 1, using the single most intuitive example there is, the potentially rigged coin. All right, let's start with a bold claim. Forget the formulas. And for now, forget the jargon. We're going to build our entire intuition around one simple, powerful question. Is your friend cheating, or are they just unlucky? Imagine this scenario. Your friend comes up to you and says, hey, this coin is 100% fair, 50-50. So you decide to test it. You flip it 10 times. And the result? Well, look at this. Head, 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 another head. All the way down, you get 9 heads and just 1 tail. Right about now, your internal BS detector is absolutely screaming. But how do you prove it? Well, the methodology is actually super intuitive. Let's walk through this logic. Step 1. We're going to start by assuming the coin is actually fair. We'll give your friend the benefit of the doubt. Step 2. Then we calculate the probability of getting a result this weird purely by luck. And that leads to the big question. Is that probability too low? If the answer is yes, we call BS. If the answer is no, well, we have to accept the result. So let's do the math. Again, the scenario. Your friend claims the coin is fair, but you got 9 heads and 1 tail. If the coin is truly fair, meaning the probability of heads is 0.5, what are the odds? First, what's the chance of getting exactly 10 heads? That's just 0.5 to the 10th power, which is about 0.00097. Tiny. Okay, what about the chance of getting exactly 9 heads? Well, that's 10 times 0.5 to the 10th power, which comes out to about 0.00976. So the total probability of getting 9 heads or more is just the sum of those two. 0.00097 plus 0.00976 gives us our magic number, 0.0107. That's it. There is only a 1.07% chance that this happened because of pure luck. So now we have our evidence. Our 1.07% is what we compare against our BS threshold. And in science, that's usually set at 5%. So is 1.07% less than 5%? Yes, it is. The result is impossible enough to reject the fair coin idea. Your friend is cheating. Now, here's the aha moment. What you just did, that entire intuitive process, is hypothesis testing. You just used different words for it. This table here is like the Rosetta Stone, mapping your intuition to the formal syntax. That thought, assume the coin is fair, that's called the null hypothesis, or H0. The idea that your friend is rigged, that's the alternative hypothesis, or H1. That 1.07% chance we calculated, that has a special name, the p-value, represented by a lowercase p. And finally, your 5% BS threshold, that's called the significance level, represented by the Greek letter alpha. And this brings us to the one universal rule that governs everything. If p is less than alpha, you reject H naught. That's the whole game. You can even visualize what rare looks like. Imagine a bar chart of all the possible outcomes. The chances of getting 9 or 10 heads would be these tiny little bars way off to the side. That's our rejection region. Of course, in the real world, you're not doing this with a calculator. You're using code. Here's how you'd solve this exact problem in Python. First, the setup. We set k equals 9 for our successes, or heads, n equals 10 for the total trials, or flips, and p equals 0.5, which is our null hypothesis of a fair coin. Then we run the test. We use the function binom test from spysci.stats. We pass in k, n, and p. And notice this last part, alternative equals greater. That's us asking the computer, what are the odds of getting 9 or more heads? And when you print the result, look at that, p-value, 0.0107, the exact same number. And just like that, you've mastered the logic. But here's the next challenge. What about data that you can't count? A coin flip is what we call discrete data. You can count the number of heads, 1, 2, 3, and so on. But you can't really count things like revenue, which could be $105.42, or time on a site, which might be 4 minutes and 32 seconds, or the weight of a product, like 12.05 grams. This is continuous data. To handle both kinds of data, we need a universal yardstick, a single tool that can measure anything. And that brings us to our next chapter, the Z-test. Let's make this concrete with the chip factory problem. Imagine you run a factory that makes potato chips. Your target is for every bag to weigh exactly 100 grams. Now, you know from years of data that the machine has a natural variation, a standard deviation, or sigma, of 5 grams. So you pull a fresh sample of 50 bags off the line, and you find that the sample average, what we call X bar, is 102 grams. Here's the million-dollar question. Is the machine broken and making heavier bags? Or is this 2-gram difference just random noise? Guessing is not an option. But you might be thinking, what if the data is weird? What if the weights of individual bags aren't a perfect bell curve? And here is the single most important concept in all of statistics. It's called the central limit theorem, and it makes a beautiful promise. Look at this diagram. On the left, you see the raw data. Your individual bags might be chaotic, skewed, messy, weird. It doesn't matter. Because if you take the averages of samples, like the average of our 50 bags, those averages will always form a perfect, predictable bell curve, every single time. This is our secret weapon. Because of this, we can use a simple formula to measure how surprising our result is. The intuition is all you need to remember. Think of it as a ratio. Z equals signal divided by noise. The signal is how far off we are. That's our sample average, X bar, minus the target, mu. The noise is how much variation is normal. That's the standard deviation, sigma, divided by the square root of our sample size, n. All this formula is really asking is, how many standard deviations away is this result? That's it. So let's run our chip factory problem through the 4-step algorithm. Step 1, formulate. Our null hypothesis, H0, is that the machine is fine. The true mean, mu, is 100. The alternative hypothesis, H1, is that the machine is broken and mu is not 100. Step 2, calibrate. We'll stick with the standard industry threshold. Our alpha is 0.05. Now for the fun part. Step 3, compute the z-score. Let's plug in the numbers. The signal is our result, 102, minus the target, 100, which is 2. Easy. The noise, which we also call the standard error, is 5 divided by the square root of 50, which comes out to about 0.707. So our z-score is 2 divided by 0.707, which is approximately 2.83. Wow. That means we are 2.83 standard deviations away from the target. So, is that a lot? Let's visualize it. If you imagine a map of all possible outcomes, a z-score of 2.83 is way out there in the tail. It's deep in the "this is really unlikely" zone. And that brings us to the final step. Step 4, decide. We take our z-score of 2.83 and convert it into a p-value. That p-value is 0.0047. Our alpha threshold, remember, was 0.05. So the final question, is 0.0047 less than 0.05? Yes, it is. Our conclusion? We reject H0. This result is too weird to be random chance. The machine is broken. Shut it down. Of course, you're never going to do this by hand. Here's the 1-minute z-test in Python. First, the inputs. Mu is 100, sigma is 5, n is 50, and our observed average, X bar, is 102. Second, we compute the signal and noise, just like before. Signal equals X bar minus mu. Noise equals sigma divided by numpy dot square root of n. Z equals signal divided by noise. Finally, we get the p-value. We use a function from SciPy called norm.cdf. The 2 times at the front is because it's a 2-tailed test. We'd be surprised if it was too high or too low. And when we print the result, look at that. Z equals 2.83 and P equals 0.0047. The exact same numbers. The code confirms our decision, but there is a huge flaw in what we just did. We cheated. Here's the impossible assumption. In our factory, we knew that sigma was 5 grams. We had years of historical data to tell us that. But in a new A/B test, How could you possibly know the standard deviation of the entire population? It doesn't exist yet. You haven't rolled out the feature. You can't know it. You have to estimate it from your small sample. And adding an estimate adds uncertainty. To handle that extra uncertainty, we need a slightly different, more powerful tool. And that brings us to the next chapter, and the true workhorse of all A/B testing, the t-test. All right, let's set the scene with a classic scenario. We'll call it the new button. Our goal is to increase the time users spend on our site. We're running a really small test, just 10 users in each group. For group A, who saw the old button, their average time was 45 seconds, with a sample standard deviation of 15. For group B, who saw the new button, their average time was 55 seconds, also with a standard deviation of 15. So we got a 10-second increase. That sounds great. But with only 10 users, is it real? To figure that out, we need our new tool, the t-statistic. And here's the good news. It's still just signal divided by noise. Look at this formula. The signal on top is just the difference in our means, x bar b minus x bar a. And the noise on the bottom, well, it looks a bit scary, but it's just combining the uncertainty from both samples. And notice the key detail. We use S, the sample estimate, not sigma, the absolute truth. That's the whole point. Okay, let's run the 4-step playbook. Step 1, formulate. Our null hypothesis, H0, is that there's no real difference. The new button does nothing. Our alternative hypothesis, H1, is that the new button does work, that the true means are not equal. Step 2, calibrate. We'll stick with our industry standard threshold. Alpha is 0.05. Now for the math. Step 3, compute the t-score. First, the signal. That's easy. 55 minus 45 is 10. Next, the noise. We take the square root of 15 squared divided by 10 plus 15 squared divided by 10. That's the square root of 22.5 plus 22.5, which is the square root of 45, which comes out to about 6.71. So, our final t-score is signal divided by noise. 10 divided by 6.71, which is about 1.49. Okay, this is the moment of truth. Step 4, decide. Our t-score is 1.49. When we convert that into a probability, we get a p-value of approximately 0.15. Our alpha threshold, remember, was 0.05. So, the big question, is 0.15 less than 0.05? No, it's not. What's our conclusion? We fail to reject H0. That 10-second improvement, it's likely just random noise. 10 seconds wasn't enough. So why did we fail? Let's look at the numbers again. Our t-score was the signal of 10 divided by the noise of 6.71. The noise was almost as big as the signal. And that's because small sample sizes, like our n equals 10, generate massive noise. So how do we fix it? How do we win this test? Well, you've really only got 2 levers to pull. Option 1, get a huge signal. Make an improvement so gigantic that it just completely dwarfs the noise. Or, the more common path, option 2, get more data. Increasing your sample size is the single most powerful way to shrink that noise term. Of course, in the real world, you just use code. Here's what the production code looks like. We import stats from SciParm. We've got our 2 lists of data, Group A and Group B, with the actual time on site values for each user. Then we call one single beautiful function, stats.ttest_ind, passing in our 2 groups. And look at the output it gives us. T equals 2.29 and P equals 0.0342. Now wait, for this data, the p-value is less than 0.05. So with this particular dataset, it would be a success. We'd have a winner. Okay, so with the t-test in our back pocket, we are now officially dangerous. We can handle continuous variables, things like time, weight, money. But what about the most common question in business? What about clicks? Did they click the button or not? That's a yes or no question. You can't average that. For that kind of data, we need one more tool. In the next chapter, we'll cover the chi-square test. Let's imagine a classic scenario. We'll call it the red button test. You're running a website and you're testing a blue Buy Now button versus a red Buy Now button. You send 100 visitors to each. In Group A, with the blue button, you get 10 sales. That's a 10% conversion rate. Not bad. But in Group B, with the red button, you get 20 sales, a 20% conversion rate. It doubled. The answer seems obvious, right? Ship the red button. But hold on. With samples this small, how do we know this isn't just a lucky fluke? Is it real? To answer that, the chi-square test gives us a brilliant new mental model. Forget signal versus noise for a moment. Instead, think about observed versus expected. Observed, which we'll call O, is simple. It's what actually happened, the raw data you collected. Expected, or E, is what the null hypothesis predicts. It's what would have happened if your change made no difference at all. The logic is simple. If there's a big gap between what you observed and what you expected, that's a real effect. If it's a small gap, it's probably just noise. So how do we measure that gap? We use the chi-square distance formula. Now, this looks a little scary, but I promise the idea is super simple. Chi squared equals the sum of O minus E squared divided by E. Let's break that down. First, O minus E. We just find the error, or the difference between what happened and what we expected. Second, we square it. This is clever. It makes all the errors positive, and it really punishes big mistakes. Third, we divide by E. This normalizes everything. A difference of 5 is a huge deal if you only expected 10, but it's a rounding error if you expected 10,000. Context matters. And finally, we sum it all up. We just add up the normalized squared error from every single cell in our experiment. Okay, let's apply this to our red button test. We have 4 steps. Step 1, formulate the hypothesis. H0 is that color doesn't matter. H1 is that color does matter. Easy. Step 2, build the observed table. This is just our raw data. For the blue button group, 10 people bought and 90 did not. For the red button group, 20 people bought and 80 did not. That's it. That's what we observed. Now for the fun part. Step 3, build the expected table. What would this table look like if the null hypothesis were true? If button color really didn't matter? Well, overall, we had 30 sales from 200 total visitors. That's an overall average conversion rate of 15%. So, if the null hypothesis is true, we would expect 15% of people in the blue group to buy. That's 15 sales. And we'd expect 15% of people in the red group to buy, another 15 sales. See, under the null hypothesis, we expect the groups to be the same. And now, step 4, compute chi-square. We just plugged the numbers from our observed and expected tables into the formula. For the blue group who bought, we observed 10, but expected 15. So that's 10 minus 15 squared divided by 15, which is 1.67. For the red group who bought, we observed 20 and expected 15. So that's 20 minus 15 squared divided by 15, which is also 1.67. Then we add in the errors from the non-buyers, and our total chi-square value comes out to about 3.92. When we convert that score to a p-value, we get 0.0477. So, the moment of truth. Is 0.0477 less than our alpha of 0.05? Yes, just barely. Our conclusion? We reject the null hypothesis. The red button really is better. Of course, in the real world, you are never going to do this by hand. You'll use code. You import chi2 contingency from scipits.stats. You create a simple list of lists for your observed table, just 10 and 90 for the blue group, 20 and 80 for the red group. You pass that to the function, and look at that output. Chi2 is 3.92, and the p-value is 0.0477. A perfect match. We won. The data proved it. The red button is better. Right? But what if one single customer had changed their mind? Let's do a reality check. In our original test, red got 20 sales, giving us a p-value of 0.0477. That was significant. Now, imagine a parallel universe where the red button got just one less sale, 19 sales instead of 20. When we rerun the numbers, our p-value jumps to 0.0763, which is not significant. One single person flipped the entire decision of the A/B test. This reveals the most important truth about this kind of data. Categorical data is low resolution. It's just a yes or a no. There's no nuance. And because of that, you need huge sample sizes to be confident in your results. All right, you've made it. You battled through z-tests, t-tests, and chi-square. You've seen the universal algorithm in action. But now we move from theory to production. This is the most important part, because here's the first thing you need to understand. You aren't a human calculator. That's not your job. Your real job is decision making. It's about knowing which tool to use, when to use it, and how to interpret the results without fooling yourself. So let's pull back the curtain and look at the God view. This is the decision matrix. If you walk away with one thing, let it be this. You just look at your data, ask the right question, and pick your tool. It's that simple. For example, in this table, let's say your data is categorical. Things like clicks, or a simple yes or no. The question you're asking is the conversion rate different? Your tool? The chi-square test. Easy. But what if your data is continuous, like time or revenue, and you're asking, is the average different? But you don't know the population standard deviation, which is like 99% of the time. Your tool is the 2-sample t-test. And for those rare cases in manufacturing or science where you have continuous data and you do know the historical population standard deviation, you ask, is the average off target? And you use the 1-sample z-test. That's it. That's the playbook. But knowing the playbook isn't enough. The pros know the traps. Let's talk about the first production pitfall, p-hacking. Here's the temptation. You launch your A/B test. You're excited. You check the dashboard every hour. Hour 1, the p-value is 0.30. Boring. Hour 2, it's 0.15. Ooh, getting closer. Hour 4, it's 0.049. Yes. Stop the test. Ship it. You just cheated. You did. Because p-values are noisy. They bounce around like crazy, especially at the beginning of a test. If you keep peaking, you're basically waiting for a random fluctuation to cross the finish line. It invalidates all the math. So what's the professional solution? It's a simple 4-step process. 1, you pre-commit. You say, I need 10,000 users for this test, not 9,999. 2, you run the test. And this is the hard part. You keep your hands off the dashboard. 3, no peeking. Seriously, it's the cardinal sin of A/B testing. And 4, you decide once. You check the p-value only at the very end when the sample size you committed to has been reached. Okay, that's the first trap. Now for the second, more subtle one. Production pitfall number 2. I call it the Google problem. Here's the scenario. You change one tiny line of code at Google scale. Your sample size is 50 million users. The result? You get a 0.001 second improvement in search speed. And because the sample size is astronomical, your p-value is less than 0.00000001. So, do you launch? This is where you have to understand the two types of significance. First, statistical significance. It asks, is the effect real? And in this case, yes. We are 99.999% sure it's not random noise. The math is screaming at you. But then there's practical significance. It asks a better question. Does it matter? And for our Google problem, the answer is no. A 0.001 second improvement is completely invisible to humans. It provides no real value. So remember this, a tiny p-value does not mean a big effect. It just means that we are very, very sure that an effect exists. It could be a tiny, useless, microscopic effect, but we are certain it's there. This leads to the production rule. You always check two things before making a decision. First, the p-value. This tells you, does the effect actually exist? It's about certainty. Second, the effect size. This tells you, is the effect big enough to care about? It's about magnitude. A good decision requires both. And with that, your 20-minute journey is complete.